In Algebra 1, you're exposed to three main types of functions: linear functions, quadratic functions, and exponential functions. You should be able to recognize whether a function is linear or quadratic or exponential if you're given a function rule, if you're given a graph, or if you're given a table. Let's look first at some function rules and see if we can determine which one's linear, which one's quadratic, and which one is exponential. Let's start first with linear function rules. A linear function is just a polynomial function with degree 1. So look for an x that's just by itself, not raised to any other exponents. When I look at my first function rule, I see an x squared. When I look at my third function rule, I see that the x is in the exponent. So it's the second function rule that represents a linear function. Let's look next for a quadratic function. You can tell a function is quadratic because there's always an x squared in it. This might seem weird to you because when you see the prefix quad, a lot of times people think about 4, but the word quadratic actually is derived from the Latin word that means square. So look for an x squared when you're dealing with a quadratic function. I always think about the fact that a square has 4 sides, and so that's why it makes sense to me that a function with an x squared in it is a quadratic function. If you look, number 1 has x squared in it, so number 1 represents a quadratic function. Finally, when looking for an exponential function, look for a function where the x is in the exponent. You can see the word exponent inside the word exponential, and when you look at number 3, the x is the exponent. So number 3 represents an exponential function. Next, let's look at the graphs of these three types of functions. Let's first look and see if we can figure out which one is a linear function. Well, if I look inside the word linear, I see the word line. So I'm looking for my function whose graph is a line. And that right here is number 6. So number 6 is the graph of a linear function. When I'm looking for a quadratic function, the shape of a quadratic function is a parabola, which looks like a U shape. It can be a U shape that opens upward or a U shape that opens downward. So when I look at number 5, I see that parabola. So number 5 represents a quadratic function. And finally, when I'm looking for an exponential function, I'm looking for a curve, but not a curve that's a parabola. This function, this graph in number 4, is a pretty good example of what an exponential function looks like. Oftentimes they start out, this is an exponential growth function. It starts out growing really slowly, and then all of a sudden it grows faster and faster and faster and becomes steeper and steeper. So number 4 is the graph of an exponential function. Finally, the most interesting way to determine whether a function is exponential, linear, or quadratic is to look at some data. So let's look at the table in number 7 and see if we can find a pattern in that data. When I look at what's happening with the inputs, I see that the inputs are just increasing by 1. So it's going to be what happens with the outputs that makes this interesting. Well, how do I get from 2.5 to 10, from 10 to 40, from 40 to 160, and from 160 to 640? Well, the pattern that I can use would be if I multiply by 4. 2.5 times 4 equals 10, 10 times 4 equals 40, 40 times 4 is 160, and 160 times 4 is 640. So this constant pattern of multiplication shows me that this table of data represents an exponential function. When I move over to the next table, I again see that my inputs are in a pattern where they're just constantly increasing by 1, but my outputs have a different pattern. How do I get from 2 to 8, from 8 to 18, from 18 to 32, and from 32 to 50? Well, at first glance, it might almost seem like there isn't a pattern. I'm not multiplying by the same thing every time. I'm not adding the same thing every time, but let's see what happens if we try to look at that pattern of addition. 2 plus 6 gives me 8. 8 plus 10 gives me 18. 18 plus 14 gives me 32. And 32 plus 18 gives me 50. So you can see that there is not a constant pattern of addition here. But let's look at my set of differences that I just got, and let's see if I can find a pattern with those differences. Well, to get from 6 to 10 is an increase of 4. To get from 10 to 14 is another increase of 4. And to get from 14 to 18 is another increase in 4. This is actually a way to tell whether or not data is quadratic. The first differences are not the same, but the second differences are equal to each other. So this table of data represents a quadratic function. So by process of elimination, I can tell that number 9 is going to be a linear function, but let's see if we can figure out why. This time my inputs aren't just going up by 1. It looks like my inputs are going up by 4 each time. Now let's look at what's happening to my outputs. To get from -5 to 7, from 7 to 19, from 19 to 31, and from 31 to 43, I see that there's a pattern of constant addition. Plus 12, plus 12, plus 12, plus 12. This pattern of constant addition is a good indication that your function's linear, but even sometimes you won't see that pattern and it still could be linear. What you really want to look at is a ratio. You want to look at the change in the y values over the change in the x values. Every time that I find the change in y over the change in x, I have 12 divided by 4, which equals 3. So really what I'm looking at to determine whether or not a function is linear is that I have a constant rate of change. So let's summarize and make sure that we can tell the difference between functions that are linear, quadratic, and exponential. When I'm looking at my equations, linear functions have a degree of 1, quadratic functions have a degree of 2, and exponential functions have the variable in the exponent. When I'm looking at a graph, my linear functions are straight lines, my quadratic functions are parabolas, and my exponential functions are curves. And finally, when I'm looking at a table of data, my linear functions have a constant rate of change. My quadratic functions have constant second differences. And my exponential functions have a constant pattern of multiplication.